In this video, we are going to use MSC Nastran to perform both a post-buckling and a nonlinear buckling analysis of a cylindrical shell. We are also going to consider geometric imperfections, as you see here on the screen. Now, this example is from the MSC Nastran Demonstration Problems Manual, Implicit Nonlinear. There is a lot in this example. I am not going to cover everything in this example, but in this other window, I will let you know exactly. Let me close this. Let me go ahead and show you the agenda for today's example. So this is what I want to cover. Like I was saying a moment ago, there is a lot that's involved in this one example. They do a lot of post-buckling analysis. There's a lot of data moving left and right. But here are the three main things I want to show you. Number one, how do you set up a linear buckling analysis? And then after this, how do you perform a post-buckling analysis while considering geometric imperfections? And then towards the end, I'll discuss how to set up a nonlinear buckling analysis with different geometric imperfections. So for today's example, we are going to be using a web application to set all of this up. Now, if you want to follow along with this exercise and you want to use today's web applications, you can go to the engineeringlab.com. Here in the top right hand corner is a blue free trial button. Click the button, fill out the form, and we'll go ahead and give you access to today's web applications. Okay, so let's go ahead and start setting up a linear buckling analysis for the cylindrical shell. Now, like I was saying at the beginning of this exercise, I'm not going to cover everything in this example. I'm not going to cover every detail. I'm going to leave it up to you to go through this example, go through the documentation and read all the fine details. So assuming you've done this, it will help you better understand this example. So let me do this. I am assuming that you already have configured this cylindrical shell for linear statics analysis. So we already have SOL 101, we have a subcase, all the loads, all the nodes and materials, that's already been configured. I am assuming you already know how to get static deflections and static stresses. Now, let's go ahead and import this bulk data file. So we come to the web app and we open the viewer, and it's in the viewer where we are going to take that bulk data file that's been configured for statics analysis. Now, we need to convert this to SOL 105, which is the buckling solution sequence. So here in the bottom left, let's click on pre. Let's go to solution sequence. Let's jump over to configure, and let's select buckling. So if we open the window on the right, we see it says SOL 105. Now we have to create a second subcase. So let's jump over to the case control command section. Here, let's create a second subcase. We'll call it 2. So for the first subcase, this is going to be the linear static subcase. And then for the second subcase, we are going to call that the buckling subcase. Now, for the buckling subcase, we have to turn on a command called stat sub. So let's jump over to commands. Let's look for stat sub. Let's turn that command on for subcase 2. So we'll go ahead and select this checkbox. Here in the bottom right, you'll notice that stat sub is now on. Let's go to configure. Let's look for stat sub in this table. And we are going to select subcase 1 for that stat sub command. So what we're saying here is, for this buckling subcase, use the results from subcase 1. use the results from subcase 1 and perform the buckling analysis. That's what we're configuring here. Okay, we're not done yet. We have to turn on the output of the buckling shapes. So how do we do that? To turn on the buckling shapes, let's go back to select, look for displacements, mark the checkbox for subcase 2. So this is going to turn on the output of the buckling shapes. They're known as eigenvectors. So that's what we did. We turn on the displacement command for subcase 2. Now, to keep the result file really small, I'm going to suppress the output of the deflections for subcase 1. So that I've deselected this checkbox. Now we'll do that for stress also. Oh, stress was not on. I'll do that for SPC forces. Let me think for, yeah, let's just turn it off for SPC forces. So here I'm turning off the displacements and the SPC forces for subcase 1. This is because the final H5 file that contains the results, I don't want that file to be 20 gigabytes big. I want it to be as small as possible, so I'm only outputting what I need. Okay, now one thing about the displacement command, by default it's going to output a lot of data to the F06 file. I don't want the F06 file to be 20 gigabytes big, so I'm going to use the plot command. The plot is going to say plot the data, output the data to the H5 file only. Do not output it to the F06 file. Okay, now we still need one more thing. We need to specify the eigenvalue setting. How do you extract the eigenvalues? So to do this, we go back to select and we turn on something called the method command. So here we'll look for method and we will go ahead and turn it on for subcase 2. And now if we jump over to configure and look at method, we have an option to select one of these eigenvalue entries, EIGR, EIGRL, EIGB. Today we'll use EIGRL. And so for this, we'll go to the bulk data section, we'll go to select entry, we'll click reset table, and then let's look for EIGRL. And the L in the entry stands for length shows. Here, let's go ahead and create an entry. And for this, we are going to specify that we want at most 16 buckling shapes or eigenvalues. So we'll type in 16 here. Here in my notes, I have a value for 0. Okay, so right. So here in my notes, they have a value of 0 for this column. But here it's just a diagnostic column. The default is 0, so we can just leave that value out. Okay, so here on the right is what that entry looks like. Let's go back to the method command. And let's go ahead and select that EIGRL entry. Now, just to make sure the format of this of all these settings is okay, we are going to click on inspect. So Nastran is going to be executed. It's going to look at the case control section, at the bulk data entries, and it's going to check if there are any immediate issues. And here we get the complete message here on the top right. Let's go ahead and do this now. Let's go to download. Here, let's go ahead and click on add HDF5 out. What I forgot to do is turn on the setting that outputs the H5 file. But there's one modification I want to make. So let's jump over to the bulk data section, entries. Let's click on, oh, here it's already on. Input is set to yes. Let me look here. Oh, this should be no. Here, what happens is, when it's set to yes, it's going to copy all of this data from the input file. It's going to copy it to the H5 file that contains the results. So if your bulk data file, if it was 5 gigabytes big, it's going to copy this data of 5 gigabytes to the H5 file. To me, that's redundant. I personally don't believe, as a developer, I don't believe that's necessary. So here, what we're going to say is do not write out this duplicate data. So we'll set that to no. And let's go ahead and go to download, and now click on upload PDF and immediately run. So now we sent off this file to run with MSC Nastran, and now it's complete. Let's go ahead and look at the results maybe. So if we look through this file, maybe we got a message here, and let's take a look at this. Oh, one thing I forgot to do. I forgot to assign loads and boundary conditions to subcase 2, so let's go ahead and do that right now. So we'll go ahead and assign the same constraints to subcase 2, and then we'll do that for loads. So we'll apply the same load to subcase 2, and then we'll run this. So I was looking at the final F06 file, and I noticed that there weren't any eigenvalues or buckling load factors. So that was kind of a clue as to something being wrong. So let's go back to the run section, go to result files, and look at the F06 file. If you don't see this data here, in this table, click on download for the model.f06 file, and then you can look at the same data I'm looking at right now. So I'm looking for this table, real eigenvalues. It's the eigenvalue column that's going to give you the buckling load factors for buckling shapes 1 through 16. Now here, let me look at the document. Let me check if they list. I don't think they do. Okay, that's okay. Here, what we can do now in the post web app, if you will, we can jump and look at different mode shapes, buckling shapes rather. So this is buckling shape 1, buckling shape 2. You notice that we have 16 buckling shapes here in total. Now, let's do this now. We are going to need the H5 file. So let me see if it's available here. Let me rerun this for a quick moment. What I want in this table is I want the H5 file listed for this example, so that's why I'm rerunning it right now. Oh, sorry, I was getting a little confused here. The name of the H5 file was being renamed, so that's part of my confusion. If you go to the advanced sections, go to final management statements, you'll notice that there is this assign statement that's on. Here it's saying turn on H5 output, but name the file this name. I don't want that, so let's go ahead and turn that off. Go to download and rerun this. And when we go and look at the result files, we'll see that that file is now named model.h5. So that would be this file here. So this is the file I want to download. So we'll go ahead and click on download. And on my desktop, in my downloads directory, I now have this file. Let's go ahead and download the bulk data file that we created. So we'll click on download. So you can download it here. So in this row, model.bdf, or you can go to download and click on this yellow button, download BDF. I'll give you the same file. So now we'll call this we'll call it 1 linear buckling. So we'll use this H5 file in the next example. We'll call this maybe linear buckling and linear buckling. And you know what? Just so we're consistent with this guide, they have a name for it. So let's go ahead and use that same name. So we'll give it this name. So we're consistent with the example. Okay then. Let's do this now. So we're done with part 1, which is the linear buckling part. So let me go ahead and look at the checklist. So we're done with part 1. And now we are going to move on to part 2, which is a post-buckling analysis that considers geometric imperfections. So let's do this now. Let's close this old window. Let's go ahead and open a new viewer. And what we're going to do in this window, we are going to set up that post-buckling analysis. So we'll select those bulk data files that we created a moment ago. Here we want to do something special. First, list all the files in this directory. If you're on Windows, you would, I forget what the exact procedure is, but I believe if you, under the file name box, I believe if you type in the asterisk and then you press the enter key, this will list all the files in the directory. If that doesn't work, I think our friend Google could help out. So here again, what we want to do is instead of showing just the bulk data files in the directory, we want to show all the files in the directory. We are going to select both the BDF and the H5 file. Remember, the H5 file contains the buckling shapes that we got a few minutes ago. So let's upload that to the viewer. Now let's go ahead and start setting up our post-buckling analysis. So how do we do this? So let's click on pre. Let's go to the case control section. Let's delete both of these subcases. And then I'm not a big fan of the title command, so let's go ahead and turn that off. Okay, now let's go ahead and create a subcase, and then we'll create a step. And then we'll number the step 1. So here, this is what the right side looks like. Now, let's do let's go ahead and make this a nonlinear statics analysis. Let's go ahead and do a few things. Let's assign our loads and boundary conditions. We'll do that first because I forgot to do that in the previous analysis. So we'll do SPC and load assignment. So this is our loads and boundary conditions. Let's go ahead and turn on a few things. Let's turn on the displacement and the applied load. So we'll go back to commands. Let's look for displacement. So here I want the displacement during the post-buckling analysis. And then I want the applied load, which is the load command. And then just so we don't make the H5 file, or rather, just so we don't make the F06 file really large, we are going to use the plot option. So you'll notice plot is here and here. A faster way to do this is by clicking on this button, reduce size of F06 file. This will automatically add the plot command. Okay, so now let me look at my information here. Let's do this. Let's give this a subtitle. So we'll call this a post-buckling analysis. Now let's go ahead and look at some other information. Okay, so let's go ahead and change the solution sequence to Sol 400. And let's go ahead and turn on a large displacement. So to do this, you go to bulk data parameters, and then you click on reset table to look at all the parameters. Look for LG disp, which is a large displacement option. Let's go ahead and set this option to 1. So now large displacement is on for the statics analysis, or the nonlinear statics analysis. We also have to create a definition for the control parameters for this analysis. So we'll go back to select and we'll look for NL step, and then we'll turn it on for step 1. And then we jump over to configure, and now we have to create an NL step entry. So let's jump over to bulk data section, select the entry, reset table, and look for NL step. So these are values that were provided in the example. So unfortunately, the exact reasons why they chose these values are not described. Sometimes they do describe why they chose these values, but sometimes they don't. So let me go ahead and configure this NL step entry. For general, they use a value of 2. I believe if you click on display, or let me look. Oh no, they use min iter is 2. Here, if you hover over the description for the minimum number of iterations, here they say when high accuracy is required, they recommend using 2. So I'm assuming that's why they use 2 in this case. Also, since the example specifies that they're using the arc length method, and this is why that we know why we're setting up the arc length method. One thing they don't describe in the example, here they use a value of 0.01 here. The example doesn't describe why they use 0.001. I'm assuming this is all being done to help maintain accuracy for this analysis. And then for NS max A, they use 60. Here, I suspect the reason they did this is because the default is 1000. Whenever you see the max number of increments, it's reduced from say 1000 to 60. That means all the fun happened in the first 60 increments, or someone's already done this analysis before. They saw that nothing really fun happens for 1000 increments. So they say, all the fun happens in the first 60 increments. So we'll set this to 60 so we save some time. That's what I'm thinking they saw here. And that's why they adjusted this to 60. Now, for this other section, we'll look for the mech flag for mechanical. Here they use the U, P, and V options. And again, the example doesn't state why they use these values for the errors. But if we look at the default values here, the default value is negative 0.01 and then 0.1 here. Here they made the error a lot smaller. So I'm assuming they are doing this. They're reducing the error tolerance to help keep accuracy during this post-buckling analysis. Okay, so we're done configuring the NL step command. Let's go to case control section. Let's select that NL step entry we configured a moment ago. Okay, so we've configured the post-buckling analysis, and we'll click on inspect just to make sure there are no problems so far. What we need to do now is add the definitions for the geometric imperfections. So let's go ahead and jump out of here. Let's go ahead and do this now. Let's add the geometric imperfection. So to do this, we need to go to advanced sections and go to file management statements. Remember that we uploaded the H5 file to the viewer. So now we have to configure Nastran to access that H5 file, and the way we do this is with an assign statement. So let's go ahead and do this. Let's turn on the assign. Let's go to configure. Let's turn on the describer A and the unit describer. So for the unit number, I'll hold off on that for now. For the describer, we are going to select the HDF5in option. And then for value 2, we're going to specify the name of the H5 file. So here's the name of that H5 file. Now for the unit number, I like to describe it as like a place. And we are going to make this data accessible through unit number 31. So now this data in the H5 file, it's going to be available to Nastran during the analysis. Okay, now we have to define the imperfection. So let's go to bulk data, go to select entry, reset table, and let's look for this imperfection geometry entry, imp geom. And let's go ahead and click on create entry. And what we want to do is the following. We want to use this table here under group 1. We'll go ahead and click on add row maybe 3 times. And let's go ahead and set this up. So if you remember, I think it might be worth uploading the original linear buckling analysis example. So let me go ahead and upload that. So this is the original linear buckling example. Now let me go and show you the right window. So remember, subcase 1 was for the statics analysis, and in subcase 2, that's the subcase that performs the buckling analysis. Subcase 2, number 2, that's very important. If we go back to the previous window, in the subcase column, we are going to say take the buckling shapes from subcase 2. So we type in 2 for this column. And then for the mode number column, we are going to say access buckling shape 1, buckling shape 2, and buckling shape 3. And now for the scale, what did they do there? In the example, so if we look here, I should point out that they use 3 different ways of describing the imperfection. So here's method 1, method 2, and then method 3. Today we are using method 3 to define the geometric imperfection for this part of the tutorial. Here they use a scale factor of 0.1646256. So what they did here, I'm not going to show you this, but what they did is the following. They combined all the buckling shapes together, and they found the maximum magnitude of the eigenvector. So this value, let me see if I can remember what the value was. Right, so the max value was 6.074389. Let me look at my notes. I think it was this value. And then what they said, okay, we want a 1 millimeter max amplitude, but we know our sum of the eigenvectors is 6.074389. And then they multiply by some A factor. You end up finding that A is equal to this value, 0.1646256, I believe. Let me see what the value was. So right, this is how they got that value. So again, they took all the buckling shapes for the linear statics analysis, and they combined all of those together. And then they saw that the max eigenvector, if you will, here, if this was displacement, this would be the largest magnitude of displacement. In this case, it's the maximum magnitude of the eigenvectors. The value was 6.07 ... And then they wanted each buckling shape to be scaled the same way, so they just said, okay, multiply this by A. How do we get 1 millimeter? And they did the math, and they eventually came to this value. So that's an idea of how they got that value. It's not explicitly stated in the documentation, so that's why I thought it'd be good to briefly describe that. Okay, so here is the scale value. So we're using 0.1646256 for each row. And now if we look at the right side, this is what that entry currently looks like. Now, we need to use this geometric imperfection in this analysis. So how do we do this? We first create a imperfection case entry. So we'll go back to select entry and click this row, imp case, and we'll create an entry here. The imp case is like a basket. We are going to take all the imperfect geometry entries we've created, and we'll add them to this case basket, if you will. Now, in the case control section, let's go to select and look for imperfect. So we'll turn on imperfect for step 1, or no, for the above subcase level. I believe in the documentation it says you have to use this command in the above subcase level. And then we'll turn on the O imperfect command also. This is going to output the imperfect, or the geometric imperfection. It's going to output that shape to the H5 file. So let's go to configure. Let's look for imperfect. So here we're going to say use that basket, imp case 1. That basket has all those imp geometry entries. So it's saying use all those geometric imperfections you defined a few moments ago. And then for O imperfect, I'll put the geometric imperfection shape. we are going to say only output that to the H5 file. So we're going to use plot, and we're going to say output that data also to the punch file. So you can either use the mouse to select the various options, or you can use the control key to select different options. So let's go ahead and select punch and plot. So again, output the imperfect shape to both the punch file and the H5 file, so the plot command. Okay, now the example uses all 16 buckling shapes, but here we've only defined 3 buckling shapes. So let's go ahead and do this. Let's add more rows, and let's go ahead and display 20 rows. So we'll click on the 20 count button here. Oh, that's the wrong. We should be clicking on this. Look to the far right, click on 20 here. So this will show you 20 rows in the table. Let's go ahead and add 5 more rows. So we should have 16 rows here for the 16 buckling shapes. So you can type in 2 and 2 for each row, or you can use this row. Type in 2 here, then click on this button, and then it applies 2 to every row. And then we'll do the same for the scale factors. So here we'll type in the value here, and we'll click apply. Then every row has the same value. Here we'll say use buckling shapes 1 through 16. So we'll manually type in these values: 10, 11, 12, 13, 14, 15, and 16. Okay, so we're done setting up. We're almost done. I forgot one critical thing. If you remember in the advanced section, the H5 file is being made available through Unit 31. So back in the imp geometry, in the unit number column, this is where we type that value 31. So we're saying source the buckling shapes from Unit 31, and Unit 31 is associated with that H5 file from the linear buckling analysis. So let's go ahead and use 31 here. Okay, let's go ahead and do a quick recap here. So I've defined imp geometry. Let's go to display selected here. So we've defined parameter with large displacement. We've defined NL step, like you see here. We've defined an imperfect geometry setting here that combines all 16 buckling shapes. We've defined an imp case that contains and is a basket for all those geometric imperfections. And then in the case control section, we defined a subcase and then a step. We've turned on and configured all these outputs and settings here. So now let's go ahead and try to run this post-buckling analysis. So we'll go to download and click on upload PDF and immediately run. Now this will take a few minutes, but let's go ahead and jump over to result files. And there's one thing I want to call out. Here on the bottom left is a button, Model STS. This is a very useful button. This is going to give you a lot of data, but the one piece of data that we want to look at are the maximum responses. Here, it's going to track what the maximum response here, in this case, is going to be the displacement. This is very useful for seeing if the displacement makes sense. So I think in this example, we're using millimeters for units of length. If the I forget how long. Let's go ahead and see what the dimensions are for the cylinder. So this cylinder has dimensions of, or rather the height is 300 millimeters. If this maximum displacement during the analysis, if the maximum displacement is 1 million millimeters, but the cylinder has a height of 300 millimeters, you know something's wrong. This cylinder is deflecting by 1 million millimeters. That's totally wrong. Here we see that the maximum displacement so far is about 0.14 millimeters, which is still in the realm of what we expect. So again, if you ever see the displacements go into the millions or billions of millimeters, If the cylinder is deforming into space in the universe, then that's kind of a big red flag telling you there's something wrong with your analysis. Here, let's go and look at the STS file. Here we see that the final deflection, the highest deflection is about 0.17077. Here there's another file, .nimo, so this stands for nonlinear iteration module output. Here we also see the same thing. Let me look here. Right. So we see something similar. Let's go and zoom in at the top. So at the very end, we get told that grid 2318 component 1 has the highest deflection. So let's go ahead and confirm that value. So we'll go ahead and jump over to the post web app. Let me make sure. Oh, wrong window. So let's go ahead and do this. Let's go to the post web app. Let's go to displacement. Let's go to navigate to the very last page, the very last row. And let's go ahead and mark this checkbox. And let's look at here. Let me see what component it was. They had component 1. So let's go back here, component 1. So we'll turn on only component 1. And then if you look at the maximum label, we get the same value, 1.708 at grid 2318 component 1, which is the X component. Okay, so let's take a look at this, because I think in this example they have an image of the post-buckling shape. So here we'll look at, right, so this example here, let's see if we can find this example, or let's see if we can replicate that example. Post-buckling shape. And let's go ahead and deform this. Okay, there is one mistake I made here. We want to take this and load it up to 1 million newtons. So we need to go to loads and BCs, and we need to make this. Let's see, what do I have here? 1000, I believe, or 10. And let's go ahead and rerun this. So again, I want to take this to very high loading. And let me look at my notes here. Right, so you might be asking, okay, where did I get the value of 10? So if you take all the, let me go ahead and show you the loads. So here's the axial loading. If you combine all of these, and then you find what scale factor gives you a million, you end up finding that it's 10. So I think if we, let's go ahead and look at that real quick. So if we look at the force entry, you see each force entry is 1111.111, and then there are over 90 of these, so times that by 90, times that by 10, and then you'll see that gives you almost 1 million newtons. So that's why I wasn't getting the same answers as the ones from the documentation. So again, that was the scale factor. So we went ahead and modified the scale factor. It's actually confirmed this was updated. So when you use that, there's going to be a load entry. So if you look at this load entry, you notice that the scale factor is automatically 10. Okay, so let's go ahead and look at the displacements. Okay, so we see the max displacement was 0.58, 53858. Let's go ahead and see what's going on here. Okay, so you can see that change, and I think I'll pause the video here because this analysis might take a minute or two. Okay, we're almost done with this post-buckling analysis. Okay, so if we look at figure 54.6, this is a post-buckling shape when we use a mixed mode imperfection of all 16 buckling shapes. So let's go ahead and jump over to this window. Let's go to navigate to the last row. So you'll notice something about the results. So during the post-buckling analysis, when you hit the final load, you end with a user fatal message. This is okay. So if we look at the post web app, let's go ahead and look at the displacement data set. Look for the very last row. So navigate to page 6, this row, and then let's go ahead and display it. So you'll notice that this image looks very similar to the post-buckling shape from the documentation. So here, let me turn on the deformation so you take a look at the deform shape. Let's go ahead and use maybe 50 for the scale factor. Too much, 30 maybe. So here we have been able to replicate the post-buckling shape that was shown in the documentation. Okay, so if you want to know what the final load was, the best way to do this is by looking in the EB06 file. And let's see if it's listed here. So you want to look at the final load, which was this load, I believe. So let me look here. So this would be your so-called limit load. So that would be this point on the plot. So that would be this orange point that you see here. That would be this value that we saw in the O load resultant. So that would be the last. You'll notice that O load resultant is repeated multiple times. So the one you want to look at is the final one. So this is telling me that the last load in this analysis was this value along the Z direction, and here the axial direction is the Z direction. So that would be our final load. So that's the end of this part. And now let's go ahead and download this data. So let's download the bulk data file, and let's download the we want the punch file in this case. So the punch file is going to be used in the next exercise. That's why I wanted to recover it here. So let's go ahead and save this to post-buckling analysis. And then just so we're consistent with the example, let's go ahead and rename these files. So I believe this example is number 3. So again, they have 3 methods, 3 different ways to describe the geometric imperfection. So method 1, 2, and 3. Here we're using method 3. I think it might be worth, let me rename these files real quick. Let me briefly describe how they set up the first and second method. So if we scroll up here, the first method of defining the imperfection is this example here. What they do is they separate out the first 10 buckling shapes and use different scale factors. So if you look, I think here we have it. Let's do this. Let's go ahead and upload the, so right now we're looking at the linear buckling shapes from the very beginning of this exercise. Here, if you look at the spectrum, it has a maximum value of 1. Okay, so what they did here in this first part, they wanted a maximum amplitude of 0.5 millimeters. So what they did is they took a buckling shape 1 and then multiplied that value of 1.0068 by 0.5, and then that gives you 0.5 millimeters. Here for this other buckling shape 8, let's go ahead and display that. The maximum value is 0.3. So what they did here is they multiplied it by this scale factor 0.3846 and so on and so on, and then that gives you a maximum amplitude of 0.5 millimeters. So that's what they did in this case. So let me briefly walk you through how to configure this geometric imperfection. So everything's the same as before, but here in the bulk data section, you go to the geometry entry. Here, what they do is this. Let's go ahead and delete all of these rows on the right side. And for this first geometric imperfection, let's go ahead and add it. So they consider subcase 2, they consider mode 1, and then they use a scale factor of 0.5. And then here on the top right, we'll create a new geometric imperfection. So that will be row 2. For the subtable, click add row. So mode or subcase 2, mode 2, and then a scale factor of 0.5. And then they do this 8 more times. So 1, 2, 3, 4, 5, 6, 7, and 8. And then we'll click on add row for all of these. And then they use 2, 2, and I'm going through this real quick. So again, this is the first method of defining the geometric imperfection. But here in this tutorial, what we did is we set up the third method that combines all 16 buckling shapes to define the geometric imperfection. And right now what we're doing is I'm showing you how to configure the first geometric imperfection that they have. Okay, so here I missed the row, but that's okay. So like you see in this example, whatever you see here, you copy it over. So they use 0.5 for all of these, I believe. Now for mode 8 and 10, they use the scale factor, mode 10 and then mode 8. And then let me confirm the mode numbers. I have mode 1, 2, and then I forgot one mode. So we'll click create entry, we'll add a row here. This is mode 3 and then 0.5. So if you look at the window with the bulk data entries, let's click on display PDF output. Here on the left is the first method of defining the geometric imperfection. Here on the right is the same setup. So I just wanted to show you how to configure the version that they had. And then of course, don't forget the unit number. So you use 31 for all of these rows. So 31, 31. So we're saying use the buckling shapes that are available in unit number 31. And then here, you see 31. So again, this is aligning to the first method where they combine 10 buckling shapes to define the geometric imperfection. Now, in the second method, one thing I forgot to do here. Remember, you have to update the basket imp case. So here, let's go and select all the geometric imperfections 1 through 10. So always remember to update the imp case command. Okay, for the second method of defining the geometric imperfection, they only consider mode 4. So how do we do that here? So I think it might be easier to just delete all of these. So let's go ahead and delete all of these. And let's create, how many do they have here? 1, 2, 3, 6. So we'll create 6. Okay, then like before, add a row, add a row. And then remember, use subcase 2, which was the buckling subcase from the very start of this exercise. And then this is all being done for buckling shape 4. So we'll use 4 for the mode number here. 4, 4, 4, and 4. And then we'll use 31. 31, 31, and 31. And then for the scale factors, let's see what they use. They use 0.2. Okay, so 0, that would mean there's no geometric imperfection. 0.2, 0.4, 0.6, 0.8, and 1. 0.8 and 1. So here's what that setup looks like, and you'll see that it matches the setup from the documentation. Now, remember, always update the imp case command. So here we'll select all 6 of these geometric imperfection entries. Now at this point, that was the second method of defining the geometric imperfection. Earlier we went over the third method, but here what I want to do in this case, let me download this example. The reason I'm downloading this example is because in the future, in a separate video, I'm going to walk you through how to create this graph. So they don't tell you exactly how to build this graph. So in a second video, I'll tell you exactly how they built this graph. Here, what I just downloaded will help you build the first, let's see, 6 lines. So 1, 2, 3, 4, 5, and 6. So this is using the second method of defining the geometric imperfection. The last line, that would be the third method of defining the geometric imperfection. So let me go ahead and do this. Let me rename this bulk data file. So we'll call this 2. So this is this model is the model we just configured. So from this window, if we open it, we'll see the same entries. So let's go and look for those entries. So here are the geometric imperfection entries. You can see that they align to the second approach, which would be this approach. So we're going to save this file again, so later on we can create the graphs in a second tutorial video. Okay, so now we are done with number 2 here. We're done with the post-buckling analysis. How do we configure a nonlinear buckling analysis? So let me get set up for that example. So let's remember that we downloaded those bulk data files that perform that post-buckling analysis using the third method of defining the geometric imperfection. Now what I'm going to do here, let me close the old windows. Let me upload those bulk data files from the post-buckling analysis. So we'll look for this directory. And then one very important detail I forgot. So in this nonlinear buckling analysis, the way they define the geometric imperfection, they use the punch file. So let me see if I can find it here. The name of the punch file is actually called something else. Here it is. Here, if you look at this row, this is the name of the file they use. NIMPF cylinder version 4.impf. So let me show you what that file looks like actually. So this is going to be the 4th way of defining the geometric imperfection. And right now, let me show you what this IMPF file looks like. So this is what the IMPF file looks like. Now, what we had during the analysis, we had a punch file created. So the punch file contains that imperfect shape. Let me see if there was actually an image of that. There isn't one. Okay, let me briefly show you what that image looks like. Let me go ahead and upload number 3. And now I have to dig for the H5 file, so let me see if I can find it real quick. Okay, so let's go ahead and upload the H5 file. So this H5 file is the file from the post-buckling analysis. So remember that we turned on this command, O imperfect. This outputs the imperfect shape for the geometry. So if we go to post, if you look under nodal imperfect, this was the imperfect or the geometric imperfection that we define with that entry imp geom. So this combination would be this shape here. If we define multiple geometric imperfections, there would be more than one row here. So if we define 10 geometric imperfections, there would be 10 rows listed in this table on the right. But here it was just the combined geometric imperfection of all 16 buckling shapes. So there's only one row here. So this shape here is now available in this punch file. We are going to convert this to this format that you see on the screen. And then we're going to use this to define a different geometric imperfection. So let me do this. Let me rename this IMPF, I think it was called. Let's go ahead and see here. Right, IMPF. So let's go ahead and open that. Now we have to reformat this a little bit. So let's do this. We'll move the cursor, this blinking line, the cursor. We'll press and I'm using Notepad++, by the way. So the Notepad++ has this really nice feature. You move the cursor here, you press and hold both the Control and the Alt key. And then with the left mouse button, you can drag and select. So here, let me repeat that. Press and hold the Control Alt keys. Move the mouse a little. Let go of the Control Alt key. And now you're in this mode where you can select vertically data. So what I want to do here is delete the last few integers from each line. So there are different ways you can do this. You could do this with Python. You could do this with a different script. You can do this with regular expression. So I'm assuming you are not familiar with these other scripting methods or with regular expressions. So here I'm doing it the brute force method, which is I'm just going line by line and I'm selecting everything that I want to delete. So let's go ahead and do that all the way to the bottom. And then here I made a mistake, so now I have to repeat this. So we'll go all the way to the bottom. And we'll delete those last few numbers. So once you selected the data you want to delete, just press delete or backspace, and you'll notice everything's been deleted. Okay, so now what's next? Let's delete the first few lines that don't do anything for us. And you can see that we're getting a little closer to this file. So this is the file that we want, and we're slowly modifying that punch file to get us there. Okay, now let's go ahead and do this. Let's delete these lines. Now, if you just select this line, if you go to the very end of that line, oh, just delete that line. So here let's do a replace. So here we're replacing every instance of this line with a blank character. And notice we still have these gaps. So there's a trick to that. Once you select up to the end of the line, move to the second line. So you notice that there's an additional character that's being selected. That's what we want. So once you do that, go and do the replace. And you notice it's actually replacing the empty line for us too. So once we're comfortable with this, we'll click on replace all. That might take a minute or two depending on how big this file is. And then there's one last thing we have to do now. We have to replace this G letter. So we're almost there. So what you could do is this. I believe you could just select all the leading blank spaces up to the letter G. And then do a replace with the empty character. And then there you go. So now you'll see that the imp file from the documentation. So we downloaded this file from the documentation. So that would be this file on the left, and then on the right, this is the file we just created here. So you notice that these values are almost identical. There are subtle differences, like this 1 here in this line, this 1 here before the letter E. It's actually a 0 on the right side. So if you zoom in for this number, this is a 0 where before it was a 1. So you'll find small differences, but that's okay. Now let's rename this file. So here they call it version 4. And now let's go ahead and start a new window. So we'll click on, so this is the last part of this entire video. So far we've gone over how to perform a linear buckling analysis. We went ahead and configured a post-buckling analysis with the third method of defining the geometric imperfection. And now for the last part, we're performing a nonlinear buckling analysis with geometric imperfections, and we're using a fourth way of defining the geometric imperfection. Basically, this file is defining a geometric imperfection. So this is the fourth method. Let's go ahead and upload these bulk data files. So we'll navigate to this directory. We'll display all the files, and then we'll go ahead and select this imp F file during upload. Let's go ahead and select upload PDF. Okay, so how do we configure a nonlinear buckling analysis? That's actually very easy. Let's go to the pre button, go to case control commands, and go to commands, and look for this command called nlbuck. And let's go ahead and turn that on for step 1. So you'll notice there's a new nlbuck command here on the right side. Let's go to configure. Here in this case, the documentation says perform the nonlinear buckling analysis for the last increment. So they use end here. So that's how you configure a nonlinear buckling analysis. There are a few additional, settings they modify here. So let's go ahead and do this. We need to define, let me look here and think about what the best procedure is for this. Since this is a nonlinear buckling analysis, we have to define the eigenvalue extraction method. So let's go to bulk, reset table. Let's look for EIGRL. It's already here. So here they say get 10 buckling shapes. So we'll go ahead and use 10 here. And then we have to turn on the method command. So let's go to select and look for method, which I believe it's not on. So let's go ahead and turn on the method command. Let's turn it on for step 1 and select that eigenvalue extraction entry. So here we're saying extract 10 buckling shapes. Let's go ahead and adjust the NL step command. So that's going to control the nonlinear procedure. NL step is here. And now in this case, they turn off the arc length method. So let's look for arc length. So the way you turn it off is you basically delete all these values here. And then what they do, it's stated in one sentence, but here they say apply the load in 50 increments. So what we'll do here, we'll look for the fixed flag, and then we'll type in a number of increments of 50. And then we'll leave the general and the mechanical options of the same values of 2 and UPV and 0.01 here. Okay, now let's talk about what the load is. So in the load, they say an axial compressive load of 250,000 newtons. So how do you get that value? So earlier I mentioned that there are 90 force entries. So if you count all the force entries, you see that there are 90 in total. So times that times a factor of 2.5, that gives you 250. So what we do here, we use that 2.5. We go to loads and BCs. Remember, let me actually type it out for you. We know we have 94 centuries and they're all this value. And then we don't know what the scale factor is yet, so I'll call it scale factor M for now. We know that we want 250,000 units, so the scale factor ends up being 2.5. So what we do here, we go to loads and BCs, we go to the load section here, we change the scale factor to 2.5. Okay, let's go and look here. What else do I have to configure? So we have the loading, we have the method, we have a nonlinear buckling is on. Right, so let's start talking about the fourth way of describing the geometric imperfection. So far in all these examples, we've been supplying the geometric imperfection by using buckling shapes found in the H5 file. Now in this case, it's a little different. Our starting geometric imperfection is sourced from this file, IMPF. So remember that file was uploaded a few moments ago, so it's available in the web app. So we also have to tell Nastran, hey, access that IMPF file. And then here for the value 1, instead of using HDF5in, you're going to say IMPFIN. So we're saying use the geometric imperfection data from this .impf file. And now if we go back to the bulk data section, let's look for that old geometric imperfection. So here, this was previously configured for an H5 file, but now we have to configure it based on this IMPF file that we have. So let's go ahead and delete. Let's just delete all these rows actually. We'll create a new row. So in this example, we don't have to worry about the subcase. There's no subcase or step to worry about. There is, let me look here. In the set 3, okay, so there is a set 3 I have to define here. Or actually, no, I think we don't have to worry about the set 3. Let me look here. Okay, I was just making a mistake, so I have to pause and look at my notes for a brief moment. You do not want to modify this table here, this subtable. What you want to modify is these fields. So here for scale factor we use 1.0, and for the unit we use 31. So here we're saying take the data available in unit number 31, which if you recall we just configured to get data from this file. Use that data, scale it by 1, and then that defines the geometric imperfection. Let's go to select entry. Make sure that for imp case you have imp geom1. And then let's see if there's anything more to configure here. Nope, I think we're ready for this nonlinear buckling analysis. Okay, let's go ahead and try and run this. So now this nonlinear buckling analysis, this is going to take a long time. So one thing you want to keep an eye out for is the STS file. So it's good to look at the displacement here, or the maximum response. Make sure that this maximum response is practical and reasonable. If we look at the maximum response here, if we hover over the point, is displacement. The maximum response so far is a displacement of 0.15 millimeters, which makes sense so far. It's within the realm. It's within the dimension of the cylinder. If the displacement ever got up to 1 million or 1 billion millimeters, you know something's wrong with the analysis. If you see something wrong here, if you click on stop, that's going to stop the Nastran run. Okay, so like I said, this analysis is going to take a minute or two. So I think at this point, I'll just pause the video and wait for this to finish. Okay, we're done with the nonlinear buckling analysis. So let's take a look at a few things. let's look at this figure, figure 54-7, buckling mode shape from nonlinear buckling analysis. So that would be this shape that you see here. So if you look at the spectrum, the highest value is a 1.155 or 1.16. And then if we look at this figure at the top right, you can see it's also a 1.16. In this case, let me look here. Let me make sure I'm looking at the right buckling mode shape. Right, so this is an eigenvector. So this is going to be, right. So this, I got my exponents. Oh, interesting. Here they got 11.6. Right, so here at the upper bound of the spectrum, they got 11.6. But here we're getting 1.6. But that's okay. I think different programs are going to number their eigenvectors a little differently. Okay, now one of the last few things you want to look at. Let me look at something else here. Right, so another confirmation here in the bottom right, the maximum eigenvector, if you will, is at grid 2022. If you look back at the documentation, here in the bottom right of this figure, they also tell you the max eigenvector is at node 2022. So here what I want to show you is that we're consistent with what the documentation is showing. But for some reason we're getting 1.16, but the documentation is getting 11.16. I'll ignore that discrepancy for now. One final confirmation. Let's confirm the final nonlinear buckling mode. So to compute the final buckling load, you need this value, alpha. So this alpha value is available in the F06 file. So let's look for that alpha value. So we'll go back to click on model.f06, search for alpha. This value may or may not be here. The reason is because we only show you the last few lines of the F06 file. If you have a very big F06 file, this alpha might be buried and out of view in this window. Here, the value alpha is listed. So we get a value of 0.25288. So that's going to be the same alpha value that we get here in the documentation. If the alpha value is absent, what you can do is download the F06 file. So click on download. And then you could download that F06 file and look for alpha here. And then you'll see the same value, 0.25288. Now, once you get that final alpha value, you use this expression. You plug in that alpha value and all the other values, and then you get a final value of 251 kilonewtons, or 251,000 newtons. So that's your final nonlinear buckling load. Now, just in case you want more information about this nonlinear buckling procedure, there's one document that's worth referring to. So let me show you what that document looks like right now. So if you go back to the MSC Nastran Service Pack 1 release guide, which is this document here, MSC Nastran 2020 Service Pack 1 release 1 guide, sorry. There is a section on nonlinear buckling. So this was the year that first made nonlinear buckling available. And this is the expression we just used. The nonlinear buckling load is equal to PM plus alpha times the load increment. So this expression again can be found. This expression here that we just used can be found in this old release guide from 2020. So I just wanted to point that out for those who are interested in reading more about this. Okay, so we are done with this fourth analysis, which is the nonlinear buckling analysis. So we'll call that complete. And now let's do this. Let's create a backup of this file. So you can either click on this row, model.bdf. you could click download, and then that would download this bulk data file, or you can go to download and click on download PDF, and that will give you the same bulk data file. Okay, so let me do this. Let me create a backup, or let me rename this file so we're consistent. So I was going to rename this bulk data file. So we just downloaded model.bdf, so we'll rename this. So we'll call this 3 nonlinear buckling, and we'll move it here. Okay, so there you have it. That is how you go through this entire exercise. So just to recap, we started off with how to set up a linear buckling analysis. The assumption is that you already configured a linear statics analysis, and then I walk you through what the process is like to configure a linear buckling analysis. Then in the second part of this video, we configured a post-buckling analysis with geometric imperfections. Now remember that the example has 3 different ways of defining the geometric imperfections. So here in the first method, they consider all 10 buckling shapes. In the second method, they only consider buckling shape 4, and then they have different scale factors. And then in the third method, they consider all 16 linear buckling shapes, all scaled differently. And so we went over how to use the third method. And then I briefly went over how to quickly configure the other two methods. And then for the third part of the video, we configured a nonlinear buckling analysis, and then there was a fourth way of specifying the geometric imperfection. So what we did was we took a punch file, that would be this punch file. We took this punch file and we converted it to this format. And then we went in the web app and we went to the advanced section, and then here's where we configured this assign statement to say, hey, instead of using the H5 file, use this IMPF file. Use this file to help configure the geometric imperfection. So this was the fourth way of specifying a geometric imperfection. We went through that. We created, or we performed the nonlinear buckling analysis, and then we found out what our final buckling load was. So let me go and list that here. So our final buckling load was about 251 kilonewtons. Nonlinear buckling load is equal to this. So that was the third part. Now here, let me end off with the last few things. All of this was done in a web browser. This web app, if you want to use this web app, it's available here at theengineeringlab.com. So you come to this page here in the top right hand corner is a blue button. Click that button, fill out the form, and then we'll go ahead and give you access to this web app so you can go ahead and practice how do you set up a linear buckling, post-buckling, and a nonlinear buckling analysis. Here, I have a list of references that I use in this example. The MSC Nastran 2020 Service Pack 1 release guide, which had these expressions. So this is that guide. These are the expressions we use for the third part of this video. The SOL 400 users guide, which had the original example. So this SOL 400 users guide contains this example. And then the nonlinear SOL 400. Oh, sorry, I mixed it up. So it's in reference 3, demonstration problems manual. This third reference contains this chapter in this example. And then just in case you want more information for nonlinear buckling that's not in Service Pack 1 release guide, you can go to this reference number 2, which is the SOL 400 users guide. Okay, now some of you might have questions. Let me leave you my contact email address here. So if you do have a question, feel free to reach out. Now, apologies that this video went kind of slow. I did practice this video a few days ago, and there are a lot of different ways you can make a mistake, and then all your answers are wrong after that. So what I wanted to do in this video was go a little slower. So again, sorry if the pace is a little slower. The reason is because I wanted to make sure that I do the steps in proper sequence so I get the expected answers throughout this video. So again, if you do have questions, please reach out to me at this email address and I'll get back to you as soon as possible. So with that, that's the end of the video. If you have feedback, comments, questions, you could post that in the YouTube comments below, or you can email me. Okay, with that, that's the end of the video. And as always, thank you for watching.